All right, so we have a rectangular piece of cardboard that measures 20 by 30. I'm just going to draw a rectangle here. Don't worry, it'll take shape. Oh, that was not good. Try that again. Here's a rectangle. There, I called it right that time. And we're going to cut corners out that are squares. And when we do so, we're going to end up folding up the sides and creating a box. So I'm going to go ahead and draw some other dashed lines here. The dashed lines here that I'm drawing this inner rectangle, which I'm going to darken in, that's going to be the base of our box, if you can visualize this. So these sides go, and then this side gets folded up. All four of those remaining sides get folded up. So when, of course, and when we cut in different lengths, we're going to get different shaped boxes. So what we want to do is figure out a volume function, and then there's definitely a goal in mind here. So if this side is x and this side is x, in fact, I'm just going to label all of these as x's. This side started out at 30, and we're cutting out two x's. We're cutting out an x from each side. So that means the length of the base here is 30 minus 2x. And by the same token, this side started out as 20. That means this is going to be 20 minus 2x. And that means that this side right here determines the height, that is x. So the volume function is length times width times height. I'm going to write the height first. And I'm just going to leave that in factored form. There's no need to multiply it out. One thing to notice, it is a third degree polynomial, so actually when we go to graph that, it's going to look like that. Now, as far as domain goes, so looking at this, the domain is controlled by the input x. Now, x is the length that we're cutting, and we know that x has to be a non-negative number. In fact, we know that x should be greater than 0. And that's because if x is equal to 0, we didn't do anything. We're just going to have this piece of cardboard here, no box. So the question is there a biggest value of x? Can x be 50 or 100? And the answer is absolutely not. Because here, let's picture the shorter side here. The shorter side is 20 inches. Well, the most I can cut in on a side is 10 before I have no box again, right? Because if I cut in 10 inches on a side, I basically kill the shorter side. So for looking at the shorter side, I can only cut in 10. Looking at the longer side, I could go up to 15, but remember, we're doing the same thing on all sides. So that means x can be no more than 10. And in fact, I'm going to leave that as less than because, oops, forgot the less than symbol. I'm going to say that's less than because, again, if you cut in x equals 10, there's no box. Now, I'll give you a moment, if you like, to fill out this table here. This is going to actually give us a good idea of what the graph is going to look like in terms of y values. So take a moment, fill out the table. If you want, you'll use your graphing calculator, whatever, and then come back and I'll just fill in these values. So go ahead. And welcome back. So when x is 0, I did just put this here as a starting point. The volume is 0. We knew that. When x is 1, we get 504 followed by 832. So you notice that as we cut in further and further, it is increasing in volume, at least until now. We have 1,008, and then 1,056, and then 1,000 even, so it's going down now. 864, 672, and 448. So there we have a good idea of what happens. So as you cut in, naturally, when you start at x equals 0, there's no box. X equals 1, you're going to have some volume. X equals 2, you have more volume. Up until about x equals 4, and then it starts to go down the other way. You cut in too much, and then all of a sudden you have a box with a smaller base and an insane height. So that's going to have less volume. And of course, the math backs that up. So now looking at the graph, so this was generated by Desmos. I encourage you to generate the same graph if you like. Notice that I had the domain set from 0 to 10 because I don't care about any other part of the graph. And notice that this maximum point is actually at 3.924. So plugging in values was not going to catch that, okay? It actually turns out that the x value is 3.924, so that is the length of the cut. And this 1056 right here is the max volume. And again, I know we talked before about this being a third degree polynomial. The reason why it only looks like this is because, again, we restricted domain. The rest of the graph does not make sense to us in terms of this problem, but if you were to graph the entire thing, there would be a piece here, and I'm thinking there would be, I think it goes like that somewhat. So that would be the rest of the third degree polynomial. But of course, like I said before, that doesn't make sense in this problem, so we didn't consider it. So hopefully that helps you solve these kind of max problems, building the function and whatnot. And of course, polynomials do have some use for us, as we can see here. And we could take this to another level at some point. We could say, well, what about building a box with cost in mind? Maybe material costs a certain amount per square foot or whatever. We could fold that in here as well to make this more of a businessy problem. So again, hopefully that was helpful, and I thank you for watching.